Okay, so this is electromagnetic induction practical skills. You can use Faraday's law to investigate magnetic flux. So first you can put two bar magnets a small distance apart, obviously with the north and south pole facing each other. A search coil. Now a search coil is just a small coil where you know the number of turns and you know the area. You connect it to a data recorder and you set the recorder to measure the induced EMF with very small time intervals. You place the search coil in the middle of the magnetic field, so the area is parallel to the surface of the magnets. Then you turn the data recorder on. You keep the coil in the same orientation, and then you immediately move the coil out of the field. Now, because you are cutting the magnetic field lines, an EMF will be induced. So the magnetic flux density through the coil changing from maximum to 0 as you remove the coil from the field. Then you use your data to plot a graph of induced EMF against time. Using Faraday's law, you can estimate the area under the graph of EMF against time. This will give you an estimate for the total flux linkage. Now, the total flux linkage is NBA or N phi. To work out B, you can use you can just rearrange the formula. So B equals N phi divided by NA. You repeat this experiment several times, and then you find the mean value for B. Okay, so let's just say you have a conducting rod of length L. It moves through a perpendicular uniform magnetic field B at a constant velocity v. Show that the EMF induced in the rod is equal to minus BVL. So it's moving at a velocity v, so therefore the displacement S is equal to velocity times time. So in this case we're writing S is equal to V delta T. The area is two lengths times together. So you've got L times the other length, which is V delta T. This gives you area. Now to work out magnetic flux, so the total magnetic flux cut through is phi, and we know that phi is BA, and so we multiply B to A, so we got BV delta T times L. Faraday's law states that an EMF is induced whenever you have so the rate of change of magnetic flux cutting. That is Faraday's law, right? So hold on. So let me just so Faraday's law is the rate of change of magnetic flux cutting, so magnetic flux. So if you look at EMF, so EMF is equal, now the Lenz's law is just minus, right? So EMF is minus the change of magnetic flux divided by change in time. Now we've worked out that phi was BV delta TL, and that is BA, but we need to multiply by N. So we've got at the top of the fraction NBA delta TL divided by delta T. Now let's assume that N is 1 and the delta T is cancelled. So therefore you end up with EMF is equal to minus BLV. Okay, so Lenz's law. Lenz's law states that the induced EMF is always in such a direction as to oppose the change that caused it. Now, a changing magnetic field induces an EMF in the coil. If the coil is part of a complete circuit, a current is induced in the same direction as the induced EMF. However, the induced current produces its own magnetic field. Now we go to Lenz's law. If the original magnetic field is getting stronger, the induced magnetic field will be in the opposite direction and try to weaken it. If the original magnetic field is getting weaker, collapsing, the induced magnetic field will be in the same direction to try to maintain it. Okay, so this is Faraday's law, right? So Faraday's law is a change in flux linkage of 1 Weber per second. Now 1 Weber is a unit of magnetic flux. So a change in flux linkage of 1 Weber per second will induce an emotive force, EMF. So it will induce an EMF, or it will induce a potential difference of 1 volt in a loop of wire. So you would write down induced EMF is proportional to the rate of change of flux linkage. So the unit of flux is Weber and flux is BA. The unit of magnetic flux density is Tesla. Okay, so if you look at these two graphs, so if on the y-axis you've got flux linkage, and if you have the x-axis as time, then the gradient will be minus EMF, because we have to take into Lenz's law into account. The Lenz's law is just a minus. So to get the EMF, you need to do minus the gradient. Okay, so if the y-axis was n phi, which is the magnetic flux linkage, if the x-axis was time, the gradient will give you the minus EMF. So the gradient on the left-hand side will give you minus EMF. So to work out the EMF, you need to do minus the gradient. If you look on the right-hand side, if the y-axis is EMF and the x-axis is time, the area under that graph will be the change in flux linkage. Because EMF is minus, just ignore the change for the moment. So EMF is equal to minus NBA divided by T. If you do EMF times T, you get NBA. The purpose of the iron core, so this is for transformers, the purpose of the iron core is to channel the magnetic flux generated by the current flowing around the primary coil, so that as much of it as possible also links the secondary coil. So first, a primary voltage drives an alternating current through the primary coil. The primary coil current produces a magnetic field which changes as the current changes. The iron core increases the strength of the magnetic field. The magnetic field passes through or cuts the secondary coil. The changing magnetic field induces a changing potential difference in the secondary coil. The induced potential difference produces an alternating current in the external circuit. Now, why? How does this happen? So the magnetic flux passing through the core is changing continuously. The metallic core is being cut by this flux, and the continuous change of flux induces EMFs in the core. In a continuous core, these induced EMFs cause currents known as eddy currents, which can heat the core and cause heating losses, heating wastage. The eddy current effect may be reduced by laminating the core instead of having a continuous solid core. The laminations are separated by very thin layers of insulator. Currents cannot flow in a conductor which is discontinuous or which has a very high resistance. Okay, so this is for AC generators. AC generators produce an alternating current through the rotation of a coil in a uniform magnetic field. Brushes and slip rings connect a rotating shaft to a fixed complete circuit at an angle when the angle theta is the angle between the coil and the normal to the field lines. The flux linkage through the coil is n phi equals NBA cos theta. So if you look at the top graph, let's just say the top graph is the flux linkage over time, where t is the period, and it is measured in Weber turns. So flux linkage is measured in Weber turns. Now it looks like a cos graph. So the EMF is equal to the differential. So when you differentiate the flux linkage with respect to time, you get the negative EMF. So EMF is the negative of so EMF is the EMF is the negative of the differential of flux linkage. So basically, to work out the EMF, you need to differentiate the top function and then negate it. So if you look at the bottom graph, the bold line is when you differentiate cos x, right? Because when you differentiate cos x, you get minus sine x, and then you flip it, the negative becomes positive, positive becomes negative. Then you would get the dotted line.